All right, let's resume our discussion. So let's recall what we have been doing in the past a few lectures on the intractability. We sort of first introduced the notion of the reduction. Basically, our key idea is that despite the fact that we are not, we may not be able to directly design an algorithm for a specific problem, but then we are able to relate the difficulties in solving one problem with solving another problem, so that we can sort of establish that one problem is easier than the other problem or the other way around. And then we started looking into a number of reductions, right? So basically, we start with the vertex cover and the independent set, and we sort of establish their equivalent. Then we sort of say that the set cover is sort of harder than the vertex cover. Set cover is harder than the vertex cover, and vertex cover is also harder than the CSP problem. CSP problem is the constraint satisfaction problem, right? So this is the landscape, and and now we are going to continue to our discussion. Today our discussion will really just be the last lecture of discussion on technical materials. On the next discussion, that's the last lecture. It will be on MP hard and intractability. Those kind of things are really just the conceptual things, right? So this is also just again, like this is the last technical lecture, and I think this is one of the most difficult lecture. So this part was the what we did last time, the SAP constraint satisfactory problem versus the independent set, right? So it was a bit intense, and today we are going to first start with a very high level conceptual idea relating to decision problems, search problem, and optimization problems, right? So often in times when you are given a problem, say you want to be able to find a vertex cover, right? So you want to be able to find a vertex cover, and you could really ask the problem in a number of ways, and then those ways are sort of interrelated, right? So you can sort of first ask the question, does there exist a vertex cover of size k, right? So this was the decision problem we referred last time, right? So the answer can only be yes or no, right? So a very good reason that we like to work on the decision problem is that we sort of make the output of all the problems to be uniform, right? All the output needs to be either yes or no, right? So this is one reason that we really want to work on the decision version of the problem. But then the decision version of the problem seems to be a bit weak because a lot of time you are not only interested in a yes and no question, you are also interested in understanding whether we can find the vertex cover of size k, right? So um, from time to time, yeah, your goal is not really only to answer the yes and no question, right? You really need to be able to find a subset that has this kind of property, so that we can continue to use this set output by the algorithm on other downstream applications, right? So be able to find out the set itself, it's an important task, right? So finally, there's also a question that whether k itself is optimal, right? So so that we can cast the problem as the optimization problem, right? So the optimization problem is really defined as, can we find a vertex cover that minimizes the sizes, right? Instead of asking the algorithm to give me a vertex cover of size 50 or 30, right, to keep trying these things, right, we just want the algorithm to directly give us an optimized solution, right? So as you can intuitively feel, right, the problem here seems to be increasingly more difficult, right? The decision problem, right, just output yes and no seems to be the easiest one. And then the search problem asks you to ask the algorithm to give you a bit of more information, right? That intuitively sounds harder. And then finally, the optimization problem asks you to really optimize the solution instead of finding just one that satisfies certain constraints, right? That seems to be the hardest. But what's interesting here is that um, the all these three problems are polynomial time reducible to each other, right? So this is the Cook reduction, the reduction that allows us to invoke the oracles or the black box multiple times, right? So this statement that we are about to show, right, is indeed establish the equivalence and provide a very sound theoretical ground for us to exclusively only focus on the decision problem for most of the time, right? Because it turns out that in case you are able to understand the structure of the decision problem, then you are able to understand the structure of the rest of the two problems, right? So our next task is to be able to show that all these three problems are polynomial time reducible to each other, and then we indeed uses a vertex cover as an example. But in general, this kind of reduction remains true for any specific instance. All right. So now we want to establish the equivalence, right? So basically, we still need to use our framework, right? So we want to establish that the decision problem is equivalent to the search problem is equivalent to optimization problem, right? So we first need to reestablish this part, right? So they are equivalent, which means that we need to show the decision problem is reducible to the search problem, and search problem is reducible to decision problem, right? So this is what we need to establish, right? So now this is the first part, right? The slides is the first part, right? So there's a vertex cover problem, basically just asks you to answer a question in a binary manner, and there's a and the search problem, we call that the find the vertex cover problem, which asks you to find the vertex cover of size less than equal to k, right? So now we sort of have the first theorem, these two reduces to each other, right? So again, when we say the equivalence or reduces to each other, there are always two directions, right? The first one of the directions is easier, right? So basically, if you are able to tell me that to help me to search for a vertex cover, then I'm able to solve the vertex, but the decision version of the vertex cover, right? So let me be more concrete, right? So if I do have a black box, right, this black box helps me to find a vertex cover of size k if it's fixed. Of course, like if the input doesn't have this kind of vertex cover, there's no way to find anything, right? So now what we can do is to do the reduction, right? We want to use this black box and solve the decision version of the vertex cover, right? So this is conceptually very simple. I'm given a graph, right? So this graph will be directly fed into the black box of the find the vertex cover problem, the black box for solving find the vertex cover problem. And you will have two behaviors, right? You will either output nothing or output a concrete subset, right? Right. So when in case it outputs nothing, then basically our decision problem solver basically knows that there doesn't exist any vertex cover of size k. So in this case, we will directly output 0, and in case the vertex cover of size k or less is found, of course, then we output just 1 here, right? So by just looking at whether this black box outputs anything, right, we can directly translate the output to a binary decision whether the vertex cover exists or not, right? So this is the straightforward direction, and the less straightforward direction would really would be the other way around, right? So in case, let me just erase everything. Erase everything. In case we are given a black box, that just tells you a yes and no, right? So this is a vertex cover black box for that outputs only a yes and no. And are we able to use this one to guide us to search for an optimum solution? Not optimum solution, search for a specific vertex cover, right? Let me just repeat, right? So I'm given a graph, right? Some sort of graph, right? This is our input, and our ultimate goal is to be able to design an algorithm for solving the find the vertex cover problem, right? That means that if the solution doesn't exist, we output nothing. If the solution exists, we need to output a specific subset, right? And then we are given a black box of the black box for solving the decision version of the problem, right? The black box can take an arbitrary graph as an input together with a parameter k and determine whether a vertex cover exists. It will only tell you whether it exists or not, right? It will only give you a binary solution, binary information, a piece of information that's really just one single bit, right? So can you just leverage this weak black box to design an algorithm that helps us to find the vertex cover the exact vertex cover, right? Right. So this is the idea, right? The text here really just outlines the idea. Let me just switch to the whiteboard and really explain the ideas in a bit of the details. So the idea works as follows. So now sort of imagine that we are given a graph, an arbitrary graph. I'm just drawing something out. Right. So this is an arbitrary graph, right? So now we have a black box. Really, if you are given an arbitrary graph, I can solve the decision version of the vertex cover problem, right? So I can only answer yes and no, right? So what I'm going to do, let me just walk you through this idea sequentially, right? What I'm going to do is really just directly. So if this were an input graph, the first step I would just directly feed this graph into the solver, right? The first step is to just feed the G into the solver, right? If somehow the solver says that it's no, there doesn't exist any vertex cover of size k, then my algorithm just directly outputs no, right? So it's really just reflect if the black box says no. Right. So the rationale here is pretty simple, right? So we already have the decision version of the solver of the decision version that tells me that you cannot find any solution no matter what, right? So you really just forward this piece of witness to as our own output, right? So we just tell the user that don't try further to find the exact vertex cover, right? In case, right, so this is the case one, right? This is case one. The original solution doesn't have any vertex cover. In case the decision solver tells me yes, right? Decision solver says yes, right? So now we saw that the business start to begin, right? So the business start to begin because we really now need to be able to find an exact subset of vertices that cover all the edges, right? So so what I'm going to do is that, right, I'm going to delete a node, an arbitrary node in the graph in G, right? So let's say I'm going to delete this node, right? After I delete this node, I'm going to draw this graph again, right? So now this graph sort of becomes disconnected, but it's fine. Then I'm going to fit into the decision, the solver for the decision version of the problem again, decision vertex cover solver, right? I'm going to feed that into again, right? So let me just repeat, right? So I'm going to delete an arbitrary node. This is an arbitrary node. Any node will work. After I delete this node, I'm going to feed into my decision my solver for the decision version of the problem again. But at this time, I asked him that whether there exists a vertex cover of size k minus 1, right? So the original question is, originally we are asking a vertex cover of size k, but now I'm just asking that whether there exists a vertex cover of size k minus 1, right? So this one is deleted, and I'm asking this new question, right? Again, could be two cases, right? So there could be case one. Case one is that the vertex covers continue to exist, and case two means that the vertex cover doesn't exist anymore in this graph, right? So let's focus on the second scenario first. It says no, right? So now, in case this happens, what can we say, right? So what can we tell is that, like, I start with some graph, right? With this kind of graph, I'm able to find the vertex cover of size k, Why is that true? Because in step one, when we directly do the query, it says yes. Otherwise, we wouldn't even proceed, right? So the original graph, in the original graph, the vertex cover of size k exists, but in the new graph, the vertex cover of size k minus 1 doesn't exist. This doesn't exist anymore. Cannot find vertex cover of size k minus 1, right? So what's happening here, right? So what we can say that, let's call this node that, what we can say is that a node will not exist in any vertex cover of size k, right? Why is that true? So let me just repeat what I'm saying here, right? So I'm trying to, so my high level goal is to trying to find an vertex cover of size k, right? So a vertex cover of size k, right? So now when I do certain operations, right, before the deletion, after the deletion, I did certain things. Then I come to the conclusion that, well, if I want to find a vertex cover of size k, I cannot include this a node, the deleted a node, this deleted node, that let's call that a node, right? So this is the implication of this statement, right? So in case after the deletion, I'm no longer able to find a vertex cover of size k minus 1, then I can conclude that the node I just deleted doesn't belong to any vertex cover of size k. And why this is true, right? Proof, right? Why this is true? So so let S, right? So let me say that let's call S be an arbitrary solution, right? So let's S to be a subset of the vertices such that its cardinality is k, at most k, and it's a vertex cover, right? So let's say that S is an arbitrary solution we look for, right? So in case S, right, it's in case the node A is part of the S, right? This is a node and this is a subset. Right, so the notation is I don't think this is the optimal notation because they all use capital fonts, but this is a node. This is a collection of multiple nodes, right? In case A is an element of S, what can we say about that? So let me just so it's frozen again. Let me just do the restart the screen. Right. So in case this is the case, this happens, we sort of want to derive the contradiction, right? So let me just draw this graph again, right? So then so this probably is the graph we were looking for, right? So so in case this A is part of the S, that basically means that the vertex cover contains k minus 1 other nodes, right? So that basically means that the after I sort of like temporarily remove S, right? The vertex cover contains k minus 1 node. Right, so basically in English, that S contains k minus 1 other nodes than A. Right. So all these other nodes, right? Let's call all these nodes V1, V2, all the way but Vk minus 1, right? So let's call this all the rest of the nodes, right? So because V1 up to Vk plus 1, Ak minus 1 together with A covers all the edges, right? So this needs to cover all the edges because of the definition that S is as a vertex cover all the edges in the original graph, right? So because we now are talking about two graphs, right? So let's be very specific. So just by the definition, the S itself covers all the edges. And S really just consists of two parts, right? All the elements that are not A and A itself, right? So, and all these elements and all these nodes, because it covers all the edges, what we can tell, right? We can tell that if I sort of like remove all the edges that connecting to A, right? If I look at all the rest of the edges, right? They need to be covered by at least one node they need to be covered by at least one node in V1 up to Vk, right? So for any edge that does not contain A as an end, right? So for any edge that's not adjacent to A, right? So sometimes we call this as adjacent to A, right? E must be covered by v1 up to vk minus 1, right? So this is really just the definition of the vertex cover of S, right? So what does that mean? That means that if I delete A together with all edges that are adjacent to A, then I would end up with a graph, right? I would end up with a graph I draw just now, right? So I would end up with a graph such that, right, it has a number of edges, right? E3, E4, E5, right? And all these edges, as I described in this statement, all these edges are covered by at least one of v1 up to vk minus 1. Right. Can you see the point here, right? So I'm just using I have really just have been using the definition, right? So what's the definition of S? It really just consists of two components, right? So anything that's not A and A itself, right? So all these nodes, if we assume that it covers all the edges, right? So everything here cover all the edges, then for any of the edges that are not adjacent, that are not covered by A, it must be covered by the other component, right? So let me just repeat, because all the edges are either covered by nodes here or nodes here, right? So let me just try to get the different color, right? Nodes here and nodes here. If an edge is not covered by the node A, then it must be covered by a node from V1 up to VK, right? So if we push this kind of observation a bit further, then basically that means that if we sort of remove all the edges that are covered by A, then all the edges should be covered by all the remaining nodes from V1 up to VK, right? So up to now, basically we sort of can see that V1 up to VK minus 1 must be a cover for the graph with the A node and together with its adjacent edges being deleted, right? So this is really just the definition. We have been just working on the definition, right? So after here, then we can just conclude that for the remaining graph and the remaining edges, each of the edges can be covered by nodes in S that are other than A, right? Now that's sort of the contradict to the output of the oracle. Now it's frozen again, so I have to restart. Sorry. Right. That sort of contradict to the oracle, the second oracle call we say, right? So now let's see the big pictures here, right? So we sort of want to claim that A doesn't belong to any vertex cover of size K, and if this were not true, if we were able to find S such that A is part of S, then we want to derive some sort of contradiction, right? So A is part of S, right? So the contradiction is really just that we will be able to find a vertex cover of size K minus 1 after we delete the node A, right? So this is contradicting to the answers from the second oracle call, right? The second oracle call really just says that if A is deleted, I'm not able to find any vertex cover of size K minus 1. But then with the assumption that if A is in any vertex cover of size K, then I'm able to construct a vertex cover of size 8K minus 1 after on the graph when where in which the node A is deleted, right? So this leads to a contradiction. Right. So the reason it leads to the contradiction is really just I'm going to use the definition, say that to argue that the rest of the nodes in S is going to cover the rest of the edges that are not adjacent to A, right? The size of the rest of the node is K minus 1, and the graph like that's formed by all the edges that are not adjacent to A is exactly the graph with the A being deleted, right? So we can conclude that we are able to find a subset of size K minus 1 to cover the rest of the graph, which contradicts to the answer to the second oracle call, right? So this is the logic, right? So with this logic, then we sort of know that basically if the decision decision version of the vertex, the solver of the decision version of the vertex cover gives you an 0, then A is not in the set we are looking for, right? So in case it gives you an 1, that's another story, right? So after we after we do the deletion, right? So our graphs looks like what? Looks like that, right? So after we do the deletion, right? So we delete this one. So and if for the remaining graph, I'm still able to find a vertex cover of size k minus 1. That basically means that there exists a vertex cover of size k that contains A. Right. So again, like if the oracle, the black box outputs 1, then we know that there exists a vertex cover of size k that contains A, right? So if it outputs 0, we know that exists no vertex cover of size k that contains A, right? So now if there exists a vertex cover of size k that contains A, we will just put A like into the part of the output, right? So let's assume this is our output. Our output set is really just called output, right? So we really just will include A as part of our output set, right? So now we are left with the graph with A being deleted, right? And then we know that you will be able to find the vertex cover. We will be able to there exists a vertex cover of size k minus 1. But we want to find that out, right? So basically, right, you can see that we are really doing a bit of the recursion, right? So now we know that there exists a vertex cover of size k minus 1 because we call the black box of the decision version of the problem and it says here, yes. And then our goal is to be able to find that. And also notice that because of the A node is deleted, right? So the size of this problem becomes n minus 1, right? The size is really, we can parameterize that by the number of nodes, right? So this is really just a smaller problem. We still want to be able to find a vertex cover, an exact vertex cover, and we do have the oracle access to the black box for solving the decision version. And now we get a smaller problem. Then we can recurse and use the same strategy again. Like we can just pick up an arbitrary node called this B and ask again that after deleting B, A, and B together, can I still find a vertex cover of size k minus 2, right? Again, like in case it answers yes, then basically that means that there exists a vertex cover that contains A and B. And in case that answers no, then basically, right, I just need to move to C and ask the same question, right? Then move to then in case 1, there exists this is yes, and case 2, this is no. Then basically I move to a different node. I ask a different question, right? So how about deleting A and C, right? Can I find a vertex cover? Right, so I just repeat, right? So basically, at some point, I know that like A and something else has to be part of the vertex cover, right? Because I know that, right? So A is all part of one vertex cover, right? That one vertex cover must have some other nodes, right? So I just try one by one. Eventually, I will get a yes, right? So maybe after I try the F's, then I get a yes. Then I will include the F. Right, then I will proceed and find the third one, and I will continue to do that, right? So basically, that sort of means that if you have this very powerful black box for solving the decision version of the problem, you can just keep asking the question, is A in the set? No. Is B in the set? Yes. Then is C in the set? You can keep asking this kind of question sequentially, right? By asking this kind of questions a polynomial number of times, you can actually just directly leverage the decision version of the black box to solve the search version of the problem, right? That's the rationale. That's the rationale between the for proving the equivalence between the decision problem and the search problem. So let me switch back to the slides and continue the discussions.